go back to thinking about the capacitor system, which is two infinite plates. Let's say that this one has charge positive, and this one has negative charge. And therefore there is an electric field between them, going from the positive charges to the negative charges. And I'm wondering about the electric potential at different points inside this capacitor. So let's say that this is point 1, and this is point 2, and so point 3 is somewhere over here. How are those electric potentials related? Potential of 1, potential at point 2, and the potential at point 3. First of all, which are the sources? Electric potential refers to a property of the sources. What are the sources in this problem? Do I need to bring some sort of test charge to 1, 2, and 3 to talk about the electric potential at that point? No, I don't. The electric potential at points 1, 2, and 3 is due to the charges that are located in the neighborhood of those points. And those charges are the positive charges on the left side of the capacitor and the negative charges on the right side. Those are the sources that we're talking about. Now, how are those potentials related? Is V1 bigger than V2? The same? Less, perhaps? Let me just write the equation starting from the potential energy, right? Which is what we did before last class. So what's the potential energy of that charge? Now we're thinking about bringing a charge to those locations. Okay? As I said, we don't need to do that, but let's just start from that hopefully familiar terrain, which is talking about the electric potential energy of a charge located at 1, 2, and 3, and so on. Because we have an equation for that. The potential energy of a charge, Q, brought inside the capacitor, is equal to the potential energy that charge Q would have when it's at the negative plate, plus Q times E times the distance between the point where you are. This is a function of D. Let me just call it S. That's the notation that we use then. So this is the potential energy of the interaction between the sources. This is U sources with some charge Q that I bring inside the capacitor. Right? So if I divide this whole thing by the charge Q that I brought, so if I take U, the potential energy of a charge Q inside the capacitor, and divide it by that charge Q, I end up with this. This quantity is what we said was the electric potential of the sources in your problem. Right? So I can write the electric potential of the sources, which are the positive and the negative plate charges on those plates. I can write those sources, the potential of those sources, as the potential on the negative plate plus the electric field multiplied by the distance from the negative plate to the point in space where you are at. Right? So S refers to the distance from the negative plate. Right? What we're calling previously D, following his suggestion. Okay? So the electric potential inside the capacitor, as you can see, changes as you move from the negative plate towards the positive plate. It changes with this quantity E times S. Right? So since S is a quantity measured from the negative plate, as you increase S, as you move away from the negative plate, then the electric potential is going up. So if you do a little plot of the distance from the negative plate, and in the y-axis you have the electric potential, right? It will look like this. And at this point, for S equals 0, that's the value of the electric potential that we have on the negative plate. And when S is equal to D, then you have a value here, which is the potential on the positive plate. So the difference between the potential on the positive plate and the negative plate is equal to E times D. Right? The potential on the positive plate is always going to be higher than the potential on the negative plate by the amount E times D, where D is the distance between the two plates of the capacitor. Right? Right? The slope of this plot, as you can see from the equation, is equal to the electric field, magnitude of the electric field. So in that capacitor, if we were to plot all the points in the space between the two plates that have the same potential, what kind of curve or what kind of surfaces would they be? Let's say that the potential of the negative plate and potential at some specific point it's arbitrary. So let's say that this is 0. And let's say that the potential on the positive plate, let's say that it's 100 volts. This is 0 volts, and this is 100 on the positive plate. If I were to plot all the points in space that have potential, say, 20 volts, where would they be? So if this is D, all of these points that have D divided by 5 distance from the negative plate, all those points should have a potential equal to 20 volts, right? And the points in space that have the same potential inside a capacitor, they form a sheet, right? Because remember, this is a three-dimensional situation. We're just looking at the projection, right? So the two capacitor plates are like this, and the point that have, say, 20 volts will be, as he said, 1/5 of the distance from the negative plate, and they are along this sheet. A sheet that is a distance of D divided by 5 from the negative plate. Okay? That's where those points are going to be. If I were to look at this in 3 dimensions,
this is what it will look like if I try to give a perspective. The surfaces where the electric potential is constant form plane sheets that are parallel to the surfaces of the capacitor. Each one of these surfaces can be labeled by its corresponding value of the electric potential. And here we have chosen the 20 volt, 40, 60, and 80 volt equipotentials. You can see that because the electric field is uniform inside a capacitor, the sheets are evenly spaced. This is a feature of the equipotentials corresponding to a uniform electric field.